Yeah, that starting sound's a cough. All right, this topic is intro thermo. Intro thermo for college. I am a complete novice, and I might make mistakes. Haha, there's an A that goes there. So please point me out in the crowd. Point out if I make any mistakes in comments or by calling me and like yelling at me. I could give you my phone number. So I find thermo is hard to me. It's so hard, but hard is relative. This is intro thermo, so later it's going to be hard. Anyway, this problem is about the coefficient of performance, and it's about what else? Having a complete refrigeration system, along with finding other things about the system that are shown here. And yeah, good job, Square. Yeah, you could see that, so we're looking for the mass flow rate of the refrigerant, and this stuff is in order. First that, then the refrigerant load, then the coefficient of performance, then the minimum power input to the compressor at when the compressor uses 3.3 kilowatts of power. All right. So let's go slow. Let's not go slow. I'm a little bit distracted right now. So step one would be to always, according to this book, it's to state some assumptions. So now, step one, state assumptions. I kind of want to just leave it at that though. State ASSPT, something like that. Aspirations. Now, in this system, there are some arbitrary things. You just say the whole thing's an ideal system, and the only locations of heat loss are here, or heat transfer are here, where there's QL dot, the heat rate flow. I think that's what it's called. On the low side, the evaporator side, and where's the other one? On the hot side, here there's also a thermal loss. Q dot high. So, all right, make the assumption that everywhere else there is no thermal leakage. So there's no thermal leakage here, and there's no thermal leakage here, and there are no thermal leakages anywhere around the rest of the routes. You draw control volumes around here and control volumes around here. Otherwise, it could even be the whole top and the whole bottom. It's situationally dependent though, so let's continue. So the assumptions are, one, only simple thermodynamics principles apply. Or this is a simple thermosystem. So just I assume everything's ideal, e.g. whatever that means. All ideal. Where thermal losses do not occur on the outside. I assume out there, just say it's like adiabatic. Meaning thermally insulated and no heat loss in these areas. Heat is Q, hooray. If you don't know what adiabatic or any of this stuff is, repeat it and write it down. What does adiabatic mean, guys? Today I'm Dora the Explorer. What does adiabatic mean? Hello, what does adiabatic mean? It means, I can't hear it, no heat loss. Wow. All right, the assumption 2 is the system's at steady state, meaning the compressor is spooled up, and the system is in kinetic movement, in constant motion. The constant, there's an M, whatever, constant system is in dynamic equilibrium. EQ, meaning that if you look to the top left, this area, there's a flow rate that's constant. Here's a constant flow rate. Here's a constant flow rate. Everything's constant. All the flow rates and heat transfer rates are constant. So there's those assumptions, and there's like arbitrarily a lot more assumptions you could make. Step 2 is to make a list of all the data and get the property of all of the states. So let's see. Here's info point 1. Refrigerants R134A. It's not an ideal gas. Not ideal. Hooray. The temperature of the system is, the refrigerated space is 35 C. So I am pretty sure that means down here it's 35 C. Whoops. Let's leave that here. Next thing, here on top there's cooling water. So there's water traveling over here, going up and down, going down first, then up, and over here, down here. Well, let's continue reading. The temperature of the cooling water is 18 Celsius. It's stated over here. And the output is, or the outlet side is 26 Celsius. So 18 at a rate of 2.5 kilograms per second. So over here, 0.25 kilograms per second. Got an uppercase G. Whoops. Next piece of information. Just write all this stuff down. Isn't that great? I'm not going to write that down. You could do that. Just work backwards. I don't want to waste time. I'd like to say it's, this part of the process is, hold on. Basic, and hopefully it is basic. Once again, I'd like to state that I could be making mistakes with things, but these are just basics. I'll let you know if I question any of the parts. So you make a list of junk, and just go down here. Where's the list of junk? There's a list of junk. Oh, let's look at this. So here's a list of junk. We have erase things. Let's cross things out. So P1 is 1.2 megapascals. Got that. Temperature 1 is 50 Celsius. Got that. Temperature 2 is something that is implied. It is the temperature over here. Wait, hold on a second. Oh my gosh. T2 of what side? Oh, this whole section is the refrigerant. Refrigerant side. So T2 is the output. Refrigerant enters the condenser and leaves at the same pressure, subcooled by 5 degrees. Subcooled. Interesting. So why do you use T saturation at 1.2 meg? Oh, okay. Oops. Let's go forward. All right. Did I get that wrong? Oh my gosh. All right. Sorry for being confusing. This says we're at the 50 Celsius point. So we're at region 1 over here. And here's region 2 over here, region 3 over here, and region 4 over here. So right now we're at region 1. The T2 is the saturation temperature because the pressure is 1.2 megapascals. Inside into it and out of it. So down here, the output pressure is 1.2 and the output temperature, it's subcooled. So oh my gosh, I don't know exactly why. Let's think about that. So first off, go to the tables, go to the subcooled tables. We're looking at refrigerant information. Refrigerant table information. So here we're at saturated water tables, going down there, and let's go down to refrigerants somewhere around here. Superheated water, hooray. Compressed liquid, hooray. Saturated meaning I think liquid form. So at the temperature, was it 30 C? 1.2 megapascals, the saturation temperature is what? Oh my gosh. Hold on, I have to think about this for a second. Ah, right. Okay, that makes sense. Hopefully that makes sense. So we already know this is the refrigerant area or section. Let's write that down as here are not region, region 0.1, PT point number 1. So all right, equals plus, I think it's delta T, subcooled. Is that right? Let's see. Yes, it's delta T subcooled. So you start off at the saturation temperature and then you subcool it by a certain amount. So here is the over here it says it's subcooled by 5 degrees, which means you find the saturation temperature, at 120 kilopascals. Is it 120? Let's see, or is it 1200? 1.2 megapascals, which is 1200 kilopascals. 1.2 megapascals. Where is it? Look around here on the table. This is saturated refrigerant. Below that is super cold. We're at 1200, which is down here, and this should be correct. Now we are looking at the temperature. The saturation temperature at 1200 kPa is 46.29. Let's double check that. .29, that's correct. So this is equal to 46.29, the saturation temperature, at 1.2 megapascals, or 1200 kilopascals. And then it's plus this thing, which is a negative value, which is 5 Celsius, centigrade, whatever. So the temperature here is 41.3. Just round this up. All right. Simple. Given, given, given. Right. All right. So over here, this area goes over there. Hooray. Now you need to find this amount of information. So the inlet water temperature, and it says at, I assume, 0.1, section 1. Is that what it is? Why not? That's section 1. Let's call it that. Section 1, 18 Celsius. Section 1, that is wrong. Oh, I'm looking at the wrong thing. Okay. We are looking here. Look at that, 18 Celsius. So that's a given. Whoops, we're actually looking up here. 18 Celsius. Because this, I think this is given. This picture is given in the problem. In problem 6101A. So we're at 18 Celsius on the water side, and the quality factor is 100% or 0%. It's 0% steam. And in other cases, you have to take into consideration the quality factor. Quality factor equals X equals 0. X is the notation. Quality factor of water at 0.1. Or on the input side. So I'm pretty sure that's what it is. Could be either this or this. Not sure exactly why one is chosen. And I think the next part is given, 26 centigrade. Let's see. All right, so this is what I'm looking for. 26 Celsius. That is given. 26C is given, and at some point we'll use the mass flow rate. MFR, mass flow rate, or M dot. So with these pieces of information, let's see what equations we need to use. So question 1. This is what you do at the start. Oh my gosh. Let's clean this up. All right, so these are the equations that we need. These are the things that we're looking for. I find this question hard anyway. Difficult for me. All right. So when the compressor consumes 3.3 kilowatts of power, and here's the compressor, and here's the work that's in, then what is the mass flow rate of the refrigerant? So find mass flow rate, which is that, of the refrigerant. That's number 1, or A. Number 2, find the refrigeration load. I think that's Q dot L, which is the heat going into the system on the low side, which is up here at the evaporator. So look, here's the heat load, which is a really strange way of saying things. There's a heat flow rate, which is over here, and it's going in. For some reason, that's called a refrigeration load. I assume it would be the maximum amount of refrigeration that could be, that the situation, that the system could handle. So either this is an ideal number, or it is, one second. All right. Yeah, fast forward to here. So the refrigeration load is the amount of heat that could be pulled out of the fridge. Amount of heat that could be pulled out of the fridge. So you have here's a fridge box. The evaporator's inside of the fridge. And heat goes from all of the food into the evaporator and gets sent out of the fridge. So during this process, if it's a non-ideal system, heat goes in. Heat goes in through the insulating walls. These walls over here are not perfectly insulating because there's no material here that in the world currently. One second. Come on. Okay, continue. Okay, so heat goes into the system. And this QL down here is the amount of heat that could be pulled out. That's it. No need to make it more complicated. So that's the number 2 thing that you need to find. Refrigeration load. Refrigeration load. Third thing, find the coefficient of performance and the minimum power input to the compressor. I don't know what this S is doing down here. Find the COP, question mark, and then for power input, W dot min, question mark, at QL, at the minimum, at the refrigeration load, so we're looking for the minimum power input to the compressor, which I assume is different than the 3.3 kilowatts. So the minimum power input at this refrigeration load. Yeah, that's what it says. So this is mix it up, get rid of this old piece of information and do that. So let's look at some equations. Start off backwards. We are looking for this. We're looking for the minimum work. What's the equation for that? Minimum load. It is this. This is what it is. Hooray. QL over coefficient of performance. That's a given equation inside the book. How do you find the coefficient of performance? What's the equation for that? Let's look. There are two coefficients of performance. One definition is here's the real coefficient of performance. The amount of heat that's taken out of low side, which is QL, divided by the amount of work that is put in by the compressor. All right. So that is the coefficient of performance, the normal coefficient of performance. And are we looking for that? Yes, we are. Yes, we are looking for that. It says it right here. It says it right here. Now the second thing, the second equation is the maximum coefficient of performance, which is under ideal conditions. So in ideal, if you could make a perfect system, the maximum performance, the maximum amount of the maximum of this ratio is this. I think that's what it's called. I think that's how it works. So this coefficient of performance max, COP max, is always, let's see what the coefficient of performance is. Coefficient of performance, the bigger the number the better, is always greater than, or I don't think it could ever be equal to, because there are losses. Even with a superconductor, even if like completely ideal technology is used, perfect technology is used, there's always frictional loss. So COP max is always higher than the COP real. So in this case, it's somewhere around 5 versus 1. And 5 is greater than 1, so it's a real system. It doesn't break the rules of thermodynamics, because the coefficient of performance is over here is not greater than the maximum. So, okay, that explains these two. Next thing, find the refrigeration load. How do you do that? What's the equation? The refrigeration load, I assume, is this equation, which is probably in the book. I don't remember it, but it's in the book, along with these other equations are in the book. So it should be on an equation sheet that you write, or that's it. This one down here is for refrigerant. This one up here is for water. So let's go forward in the process. Okay, I can make a block. That's what we'll do. Let's do that. All right, so you start here. What knowns could we use? Let's find the known table. Here are all the knowns. Let's copy that. That should be somewhere else. Where else is it? Let's copy that from here. All right. Am I missing something? Oh yeah, I am. Okay, there we are. Here you are. Now you don't need to cheat, even though you saw all that stuff. So what knowns can we use? Here are all the knowns. First, you start off answering the questions that they ask in order. So find the mass flow rate of the refrigerant. So in order to do that, for some reason, according to these equations, where are the equations? Oh my gosh. Okay. So for some reason, we need to get enthalpy. Let's see what equation makes us need that. So, Oh man, I don't even know. Let's see. Why do we do that? Oh, come on. Think. All right. We don't know the heat out, so that's why. So here's equation 1. You don't know the heat out, so find the heat out. There's the equation for it. Use the enthalpy of the water at each of the points. So the enthalpy of the water at each of the points is here. Here's point 2, here's point 1. And you find the enthalpy inside the tables, inside the steam tables. So let's go over to the steam tables. Let's copy this. Come on, steam tables, where are you? Wait a second. Are we using steam tables? We're not using steam tables. I forgot. This is the refrigerant side. Refrigerant. All right. Let's put that there, and let's put that there. Oh, me. I'm falling asleep. It's 1 a.m. Oh, my gosh. Oh, my Lord. All right, so we're at... Is that right? Let's see. Let's look for that. So, I forgot. I forgot to paste. Come on. Nope. That's pretty cool. So we are looking for at 1.2 megapascals. I think this is the wrong area. Let's go to a different area. Here we are. We're not superheated refrigerant. Where are we? Saturated refrigerant. Saturated refrigerant. Pressure. So this is a pressure table. Do we want a pressure table? No, I think we want a temperature table. Yeah, I'm pretty sure that's what we want. Okay, so yeah, I think this is it. All right, so number 1, what's the enthalpy at those 2 points? 1.2 megapascals and 50 centigrade. So here's close enough to 50. Let's find the enthalpy. Where's enthalpy? I assume it's saturated liquid. It's not. Oh, wait a second. Is it liquid or is it vapor? Let's double check that. Is it saturated liquid or vapor? Looking. So it starts off saturated as a saturated liquid. Imagine this is what it looks like in there. It's a saturated liquid as opposed to a superheated, which is all just gas particles everywhere. Liquid, right. So we're doing this. Hey, it loaded finally. Okay, so we're looking at the saturated refrigerant table. And let's put this over here at 50 Celsius. Let's see if the enthalpy is right. One more time. We're looking at an enthalpy of 278.28. Let's see if we have that. Let's highlight 50C, around 50C, and 40C. So here's around 50. And then where's 40? And then here is 40. Is that right? We're looking for 278.28 at 50. It's a saturated vapor. Saturated. Oh my gosh. Come on, man. So we're looking for something around 278.28. We're at 50 degrees. It should be 278.28. 278.28. Oh man, am I looking at the wrong table? Come on. Come on. Is it down here? No, it's one of those. Starts off as a high pressure, so I assume it would be liquid. Oh man, come on. Wherever it is, I don't care what it is. Don't want to waste your time. Somehow the enthalpy at 1.2 megapascals, 50 degrees, 1.2 megapascals. If you look over here, it looks like I have something wrong. Here's 1.2 megapascals. Ah, right. Okay, so here's the saturation temperature. Let's get that. Let's bring that over here. Probably paste. All right, so here you are, 50 Celsius. Here, the temperature is above the saturation temperature, which means that, great. Doesn't it mean that it's superheated? Oh my gosh, come on. Let's go to the superheated tables. There's temperature, this is wrong. Temperature, all right, 1.2 megapascals. All right, here we are. Let's paste that one more time. All right, 1.2 megapascals, 50 degrees. Enthalpy, where's the enthalpy? Here's enthalpy. Here's enthalpy, 278.28. Hooray, there's the right table. Here it's subcooled. Let's see if the enthalpy's there. Saturation temperature is 46.29, so we do not use that because the temperature is below the saturation temperature. T2 is less than Tsat, so use supercooled. Use supercooled. All right, man, it's taking so long. So let's go over that table. Where's the table? We're using a supercooled table, superheated. Oh no, we're not using superheated. We're using a saturated refrigerant because it can't all be liquid. If the thing was all liquid here, just all liquid, and the compressor tries to suck that in, it'll freeze up. The piston over, I don't know, there's a picture somewhere, it would freeze up, that's all. All right, we're looking for 1.2 megapascals. Here we are, finally. this is wrong. We're looking for this stuff. Enthalpy is 110.19. Where's the enthalpy? It's either this or this. So here's the F, here's the G, here's the F, G. Here's fluid, whatever fluid is. Here's gas, gas fraction, even though fluid should be liquid. 110.19. Okay, now what's happening here? Where's the 110.19? Does it say it ends up super cold? Is that what it says? Let's see. Subcooled. Subcooled. It's not super cold, it's subcooled by 5 Celsius. Am I here? Is that where I am? Yes, it is. Okay, let's try to make sense of that. So here's the subcooled temperature, here's subcooled temperature. Here I'm pretty sure. So this is a pressure table. Do we need a pressure table? No, I think we need, do we need, oh my gosh, come on. I think we need a temperature table. Here we are. That's what it is. And we are looking for enthalpy, which is here, of a saturated liquid. Is that what it is? Or are we looking at a saturated vapor? Oh man. Whoops. We're looking for this. Here's the enthalpy table. At 52 degrees. And the value is we're not 52. What am I talking about? I'm looking at the wrong place. Here we are. Oh man. Here's the correct enthalpy table. Here it is, and we are looking in this region. Temperature 41 Celsius. This is close enough to 41, so the value should be a little bit bigger, greater. We're at 110, and that is right. So the enthalpy, H2, is somewhere between 108.28 and 111.28. So you extrapolate that. I would just be lazy and do this. So for every degree here, every 2 degrees, the enthalpy changes by this much. So the difference here is 3 degrees. No, 3 kilojoules per kilogram. Yeah, that's what it is. Okay. Okay, I've almost earned my sleep. Break time. So if it's 3 degrees, 3 divided by 2 equals 1.5 kilojoules, not 3 degrees, per kilogram. So add that to that, and the value that you get is 109.78 kilojoules per Kelvin. No, per kilogram. Oh, come on. kg. Okay, and is that close enough to the number that they use? Apparently not. Apparently they get a different number. I assume that's because I just did a linear relationship and they did something different. So that's where you get that one. Same thing for here. Let's just skip that. I'm just tired of this. You look at the, let's find it. Let's find it on the tables. All right, let's go to the water tables. Hooray. And what state is this in? What state is water in? Is it liquid, gas, or solid? Huh? Say it out loud. Use your voice, because that makes you remember things better. I am pretty sure it's in the liquid phase, because there's maximum thermal transfer in liquid phase. And I think that's what it says over here. Cooling water here at 18 degrees Celsius. And, you know, water boils at 100 and it freezes at 0. I'm falling asleep here. So let's find the, I think it's called saturated water table. Are we using a superheated water table, a saturated water table? What kind of water table? Is it superheated water? Is water at whatever it is, around 30 Celsius? Is that superheated? Super cold? Or saturated? Huh? At standard temperature and pressure at 1 atm, I think you assume, let's see what the pressure is. Let's just paste that. The pressure of the water is just disregarded, so it's negligible. It's atmospheric pressure. So at atmospheric pressure, saturated water is liquid water. Saturated means liquid. Or wait, shoot. Saturated means it could be liquid and gas. Super cool means liquid. Saturated means liquid plus gas. Superheated means all gas. So here's 3 boxes. So which one of these is which? Here, this is all liquid. This is all gas. Little specks of what? Water. And here is gas plus liquid. Which one's which? Look at it. This one is there. This is saturated. This is superheated. S heat. And here is super cooled. Super cool. Look at that guy. Look at him. He's so cool. Okay, continuing. So we are using temperatures 30 Celsius. Let's see what table we use. Do we use this one? It's not superheated, so no. Come on, Dora the Explorer fans. Say no. Do we use this one? Do we use the superheated table, guys? No. Kids. So it needs to be like 5 kids saying no. All right. Everyone that's watching this, all of you at the same time, have to say no. Swiper, no swiping. Superheated. Swiper, no. Swiping. Look, I'm swiping on my iPad. Where's super cold? Come on, man. Oh, man. Saturated water. Is that what it is? We are looking 18 Celsius and 26 Celsius. And atmospheric pressure. Atmospheric pressure. Here we are. So these temperatures are in between the table temperatures, and over here these values are ballpark around it. So here's 15 degrees, and here's, well, let's just copy that over. We'll copy that and move it over. Copy. Paste. Whoops. So this is what we're looking at. We're looking at 15 degrees and 25 degrees. So the numbers that we have down there, well, let's move this over. Here for the enthalpy, look here, specific volume, internal energy, enthalpy, entropy. 75 is between these two numbers. 109 is between these two numbers. The way that they do that is they linearize things. Let's say here, interpolate at, let's say T versus H. T, H. H and T. I think that's how it is. Either it's that way or it's this way. T, H. I'm not sure which. Let's say it's this way. Nah, let's do the other way. Because generally temperature is on the vertical axis. So say this is not 0. This is, I don't know what it is. At 15 degrees and at 20 degrees, you have certain enthalpies of whatever, 0.1, 0.2. You just linearize, find the thing in between. Look it up. So here there are 5 points. And then if you go over to the other side, look here, 83 minus 62.9, whatever that is, divide by 5 equals the enthalpy H per Kelvin, enthalpy per Kelvin. And then that's it. You just add a bunch of degrees on, and then you get that other number. Okay, next. That's that. That's all the data. Is there anything else there? Let's continue. So there, table is filled. MFO. Okay, let's find the mass flow rate. That's the next thing, is find the mass flow rate. Use the mass flow rate equation of the refrigerant. Here it is. Same as this equation, except here we don't know this, and we know this, we know this, and we know this. This is for water, and this is for refrigerant, and they are equal to each other. So there, use this equation, get the values. Here it is, here are the values. Look at that, look at all these values. There is the mass flow rate. Look at that, kilograms per second. And over here, if you enter data for the water side, you get these numbers, and look at that. Here's your heat rate on the high side. Oh man, I'm just too tired. All the other stuff should be, you know, this is general basic stuff. General basic. Just look at the rest. I'm too tired. This is taking so long. There you are. Look at that. Look at all that stuff. And here's a picture that somebody drew. Let's say I typed this out, okay? I typed all this out. You do this, then 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 you do this. Hooray. Done. I'm going to sleep. It's 1:34. Good night. Sleep tight. Here's me in a bed. It's like a off sideways bed. Now it's like a table. Okay, let's see how we can do this. Here's the bed. Here's my window. Let's make it a big window. Here's my window. And then here's the moon. Look at that beautiful moon. Oh, and here's me. I'm sleeping. I'm about to go to sleep. I got my stick legs and I got my stick bed legs.